Okay, so logarithmic functions is our next lesson. And before we get started, I want us to go back and think of some functions that we are very comfortable with. Logarithmics and exponentials are related to exponents, but not necessarily the same. They have many similar features. Gentlemen in the back, open your notebooks and your laptops because there's nothing on the TV or board. So you're not just going to stare at me. Thank you. Okay, so for exponents, like when we worked with polynomials, we usually had the base be some kind of variable, and our exponents were always a number or an integer, right? And when we talk about inverse, inverse refers to the opposite of the opposite function. What would undo a square, for example? The opposite of a square is a square root, right? And if I have a cube as an exponent, then the opposite would be a cube root of x. When we work with trig in our last unit, we had cosine of an angle. The opposite or the inverse of a cosine is cosine inverse of adjacent over hypotenuse, right? And the reason this is true is because the cos of an angle is the ratio adjacent over hypotenuse. So our function here is the cosine, and the inverse of the cosine is what would undo it. Okay, so this is just kind of let's remember what we already know, because today what we are learning is the inverse of an exponential. So the inverse of an exponential is a logarithmic graph, and I'm going to get to what it looks like in just a moment. The first thing we're going to look at are what is some review stuff that we should know from previous lessons and previous classes. The first thing is that when we're looking at an inverse function, we are looking for functions that are one-to-one, meaning they pass the vertical line test and they pass the horizontal line test. So if you have something that looks like this, I can draw a line anywhere and it only crosses the function at one point. I can draw a vertical line anywhere and it only crosses the pink line at one point. So that's the vertical line test and the horizontal line test. No matter where you are on the function, you only want to cross it one time. And since we're talking about exponentials, from lesson, where did we do this? Lesson 2 and 3, we know that we have a growth graph, an exponential growth, or an exponential decay, and both of them pass the vertical and horizontal line test. No matter where I draw the horizontal or vertical line, I only cross that exponential one time. So it is one-to-one. So our first requirement is met. The second is when we are identifying an inverse function, we usually have like a little -1 to identify that it is the inverse, just as how we saw in the cosine, right? And when we do that, what we're doing logistically is we are swapping the positions of x and y in the equation. Okay, so let's take a look at a really simple example. If we have the function f of x is y equals mx plus b, we know this equation really well. F inverse of x would be x equals my plus b. We are changing the positions of the x and y variables, and then we want to rearrange to get y equals again, but you will see that the equation will look slightly different. This is the inverse function of a line. Right? So all the variables are still there, they're all the same, but when we do an inverse, we're swapping the position and we're solving for y. And this is just a quick example of how we can do that with a line function. Okay, now because we are swapping the x's and the y's, the next two statements are important. Whatever your domain was for the regular function f, that becomes the range of the inverse, right? Because we're swapping x and y. And same with the range of f, now is the domain of inverse f. They're backwards. Okay. Now, visually speaking, and we're going to do lots more of this tomorrow when we talk about the graphing of these functions, but visually speaking, what we are doing is reflecting the graph over the line y equals x, which is a diagonal line. So if this is our graph, the pink line represents y equals x, so 1, 1, 2, 2, 3, 3, 4, 4. Whatever the picture is that we're looking at, it's like we're folding the graph over on the pink line, and we're just reflecting it over that line. So rather than a reflection around y, which is backwards, or around x, which is upside down, we're folding it over the diagonal, flipping it over the diagonal. Okay, so what does that look like when we are working with exponential functions? We learned in lesson 2 and 3 that this is an exponential function. Y equals a base that is a number raised to the power x. It is a one-to-one function, as we drew our little sketch here in the corner. So then the inverse is where we have x equals b to the y. And what we want to do today is to rearrange this to get it into y equals format. Okay? So the inverse function of an exponential is called a logarithmic function with base b. So the base of the exponential becomes the base of the logarithm. There's that kind of logistical symmetry. Now, all the rules that applied to the exponential functions also apply to logarithms, right? So we said that when we're talking about the base of the function, we need a positive number. And the positive number cannot be 1 because that's not an exponential. 1 to the power anything is just going to give us a flat line. We don't want a flat line. We want growth or decay. So as long as it's positive and as long as it's not 1, b is satisfied. Bless you. So the base of the log is satisfied. So this is what it will look like. The log of a base, the same base as in our exponential. So this is what the inverse looks like when we are doing logarithmic functions. This is what we call exponential form because it has an exponent in it. And this is what we call logarithmic form. These two things are equivalent. Okay, because we have here y is in the exponent and x is by the logarithm. So these are both inverse functions. One is written in exponential form and one is written in logarithmic form. Now remember when we did the word problems, we talked about the pH scale and how it's a base 10 system. But when we talk about the pH of different fluids, we're talking about, well, it's pH 3 or pH 8. But we know that it's a base 10 scale. So really we should be saying it's 10 to the 8 or 10 to the 7 or whatever. And same with the Richter scale when we're talking about earthquakes, right? We say it's an earthquake magnitude 8, but really what we're saying is 10 to the 8, right? So base 10 is implied in some of these scales, and we are going to use that system for a base 10. If you see a function written without a little bit of a base here next to the log, we will always assume that the base is 10. Okay, because we know how to work with base 10 systems. Okay, if the base is not 10, then the b value should be something else. It should be, the number of the base should be in here. But if you don't see a base, then we are going to assume that the base is 10. So let's take a look at some examples. In the first example, it says change the logarithmic function into an exponential function. So remember that the base of the log is the base of the exponent. The inside of the log will stay, and whatever's on the other side of the equal sign becomes the exponent. So I'm taking this base and putting it here. This becomes the exponent, and this becomes the result. So this is 2 equals 4 to the power 1/2. And if we remember our exponent rules, whenever we have a fraction in the exponent, this actually represents a square root. 4, which is 2, so that's correct. Okay. So when we're converting, the inside of the log becomes the result. So this is 1/8 equals. The base of the log becomes the base of the exponential. And whatever's on the other side becomes the exponent. So if I were to rewrite this again using exponent laws, this is 1/2 to the 3, which is the same as 1/8. So this is also correct. Okay, so we're just practicing going back and forth between the two ways of writing exponentials and logs. They're inverses of each other. So now it's asking us to go backwards, change the exponential and make it into logarithmic in logarithmic form. So now the base of the exponential becomes the base of my log. The result goes inside of my log. You don't always need to use brackets, especially if you're dealing with numbers, but you'll see on the next page that once the stuff inside gets more complicated, we will need brackets. Okay, and then what's left over on the other side is the exponent. So this is how we're going backwards. The exponent becomes the result, -2 equals. The base of the exponential becomes the base of the log. And what used to be the result goes inside of the log. So remember, base of exponential is base of the log. If it was a log and you're transforming it, then the result becomes the exponent. If it's an exponential that you're changing into a log, then the exponent becomes the result. Okay. So now it says determine the numerical value, means simplify into one number. What is this value? So in order to be able to do this, what I'm going to say is let's just make this equal x. I want to know what does this equal in simple terms. And the way that I'm going to do that is by transforming this into exponentials. And then I'm going to try using exponent laws to solve this. So the inside becomes the result. The base of the log is the base of the exponential, and whatever's on the other side becomes the exponent. So I have here 8 equals 4 to the power x. Now I can't use any exponent laws to solve this, right? This is not helpful. However, I can change the bases. I can rewrite this so that I have an exponent with the same base. What do these two both have in common? Yeah, we can rewrite these as powers of 2. 8 is 2 to the power 3, and 4 is 2 to the power 2. And then I can use my power of a power rule, right? This is 2 to the 3 equals 2 to the 2x. And when I have two exponents that are equal to each other with the same base, then I can just say, okay, well, this must mean that 3 and 2x must be the same. So the answer is 3/2. So 3/2 is the same thing as log base 4 of 8. Okay, so when we're simplifying, When we're trying to evaluate what is the numerical value, we are going to say, I don't know. And when I don't know, I put X for what I don't know. I rearrange it and I try to find and use laws that I am familiar with. So if I rearrange this, this will give me 9 equals 27 to the power X. I recognize that 27 and 9 have a base 3 in common. So this is 3 squared equals, what's 27? 3 cubed. So this is telling me that 3 squared must equal 3 to the x. I have 2 exponents, or I guess 2 exponentials. One's an exponential, one's an exponent, but whatever. They have the same base, so I can equate the exponents. So this is 2 equals 3 to the x, sorry, 3x, which means the answer is 2 over 3. This is the value of log 27/9. Okay, so we're solving for x, essentially. Any questions, comments, concerns? Okay. Today's lesson is in 2 parts. Part 1 is done. How to transform and use logarithmics and exponentials. The last thing we're going to do today is talk about the domain of exponentials and logarithmic functions. Here is a really ugly log. The base of the log is x minus 1, and the inside of the log is x plus 2. So we want to find the domain, and the way that we're going to do that is by identifying the restrictions that we already know. When we are looking at an exponential or a logarithmic function, we know from here, oh, I guess I should use a different color here, that when this is the generic one, we must have that the base is a positive number that cannot be 1, and the inside of the function has to be a positive number as well, greater than 0. Okay, these are restrictions that are true for exponentials and for logarithmic functions. So we're going to use them to figure out what can x be and what can x not be. And we're going to do it one step at a time. So here's my base. Here's my inside function. I'm going to start with the base here. X minus 1 equals b. That is the base. I know that x minus 1 must be bigger than 0. So x must be bigger than 1. This is one restriction of my domain. I have to have x bigger than 1 in this case. I also know that b cannot be 1. So that means x minus 1, maybe I'll do this in a different color, blue. X minus 1 cannot be 1. So again, I solve for x. That means x cannot be 2. I have another restriction. Okay. And my last one is looking at the inside of the function. The inside of the function must be a positive number. So x plus 2 must be greater than 0. So then x must be greater than negative 2. So I have 3 restrictions here. When we go to do a domain of a function that has multiple restrictions, we only use the part of the domain where there is overlap. So as a visual representation, I'm going to draw a number line here with 0 in the middle. And I'm just going to go, up to 3. Minus 2, minus 3. 1, 2, 3. Actually, I'm going to draw these ones over top. There. Okay. So in my first restriction, I see that f has to be greater than 1, but it cannot be 1. It has to be strictly greater than. So I'm going to draw a circle under a 1, saying that's my starting point. And I must be greater than, so I'm going to draw an arrow to the right. That is my first restriction. My second restriction says I cannot be 2. So I'm going to draw an empty circle under the number 2. It's a hole. I cannot be 2. And for my last restriction, I have to be greater than -2, but not equal to it. So again, I'm going to draw an empty circle under the 2. I have to be greater than, so it means I'm going to the right. So the domain of this function is where everything overlaps together. I cannot use anything here because there is no overlap. And I cannot use +2 because there is no overlap. They don't all agree. But what I can do is say, okay, well, I have overlap here and I have overlap here. So my domain is going to be written as the following. X must be greater than 1 with the exception of the number 2, means it cannot be 2. It can be 2.1, it can be 1.99, but it cannot be 2. So it can, as long as it's greater than 1 and is not exactly 2, then we have a domain that has an overlap and there's no restrictions that are violated. Okay, so domain is a little bit tricky, but as long as you remember these 3 rules, you can always check them. The inside of the function has to be positive. The base also needs to be positive and it can't be 1. So the base will usually give you 2 restrictions and the inside will give you 1 restriction. And as long as you can see, or you don't even have to draw this, right? This is just a visual demonstration for the purpose of our notes. But if you can just make a list and from this list, identify where the overlap is, you can just write your domain. Okay. All right. Today's homework is 76 questions. Miss Gordon, how could you? Oh, I can't see it on my thing. Let me go here. Let me see. It is this page here. Okay. My recommendation to you, do the odds if you want, do every other one. I would also start with the harder questions. So start in number 5 area. Mute. Who's unmuted? Mute your mics. Okay. I would try like the bottom 4 first. And then move backwards. Try like the bottom 6 from question 4. And then go backwards and try the bottom 6 of question 3. And then try the bottom 4 from question 2 and question 1. Okay, go to the back end of the page, work your way up. Start with the harder questions and work backwards to the easier ones. I also apologize. You will notice that lesson 6 homework is right after. I put it in the wrong spot. So you're only doing 2 pages. So from questions 1 to 5 is today's homework. Anything after question 5, that's lesson 6, that's for tomorrow. Okay. All right, that's it. You got the rest of class to work.